Right now, the industry is flooded with fragile AI wrappers and toy demos. They look incredible in a sandbox, but the moment you expose them to a messy, multi-step enterprise workflow, the system shatters on contact with reality. Almost every early AI deployment relies on the same naive architecture. You take user input, shove all your company's data into a single vector database, a system that stores information as mathematical arrays to search by conceptual similarity, feed the results to a large language model, and stream the raw text back to the user. This setup relies on two fatal assumptions. First, it assumes that all enterprise data, from conversational meeting transcripts to rigid financial records, belongs in one semantic index. Second, it assumes that delivering an AI feature simply means streaming raw text tokens into a chat window. Forcing structured CRM data into unstructured vector embeddings destroys your ability to reliably filter by metadata. If a user asks for assets strictly located in Texas with a capacity over 10,000 pounds, a purely semantic search often rejects the strict logic, returning matches that sound similar but fail the hard numerical constraints. When the model formulates its answer, streaming its raw internal reasoning creates visual chaos. Imagine a financial advisor sharing their screen during a client presentation, only to have the assistant's diagnostic logs and JSON blocks spilling onto the screen, burying the actual interface. Surviving real workflows requires replacing that single monolithic index with a deterministic search router. The presentation layer must also evolve, replacing the text streaming chat UI with dual-channel structured streaming. True enterprise AI is not achieved by buying a larger context window or prompting a smarter model. It requires building a deterministic system around a probabilistic model. Consider a highly specific, real-world enterprise query. Find forklift in Texas with 10,000 plus capacity under active warranty. This request is packed with conflicting constraints. It contains semantic concepts like forklifts, geographic constraints like Texas, numeric thresholds, and Boolean states like active warranty. A pure vector database fails to process this accurately because it cannot handle strict numeric bounds and status filters. It retrieves text that is conceptually close but ignores the hard limits. Conversely, a pure SQL database fails because it lacks semantic flexibility. If a sales rep types forklift, but the database uses the term material handler, the query returns 0 results. If an engineer attempts to solve this by duplicating structured CRM data into a vector store to gain semantic search, they invite data drift. You end up maintaining two separate indexing pipelines that will inevitably fall out of sync. The architectural solution is a unified search service. Instead of a single database, this is a deterministic dispatcher that routes the query down one of 3 parallel paths. Rather than relying on flaky AI to make routing decisions, this dispatcher uses explicit deterministic keyword heuristics to evaluate the query and select the appropriate backend. The first path handles structured CRM queries, routing them to Azure AI Search. Here, individual records are embedded into 4 specialized vectors, such as profile, experience, specifications, and general description. This multi-vector scoring pairs with reciprocal rank fusion. Reciprocal rank fusion is a technique that merges multiple search result lists into a single optimized ranking. This allows the system to natively handle faceted filters without losing semantic nuance. The second path targets transcript similarity queries, routing them directly to Postgres using the pgvector extension. pgvector is an open-source extension that allows Postgres databases to natively store and query vector embeddings. The operational advantage here is that the data stays exactly where it already lives. There is no need to extract, duplicate, and maintain parallel indexing pipelines for massive volumes of conversational data. The third path is the live CRM API, acting as a real-time escape hatch by completely bypassing the index databases. This route is triggered when data freshness is absolutely non-negotiable, and the system suspects the indexed view might be stale. The unified search service then pulls the disparate responses from whichever path it chose and unifies them into a single, predictable schema for the language model to compute. Unified search in an enterprise does not mean a single index. It means a single router that respects the native shape, location, and latency requirements of diverse datasets. Having reliable data in the backend only matters if you can deliver it effectively. How data is presented to the user requires the exact same level of architectural discipline. The standard chatbot approach is to open a WebSocket connection and blindly forward text tokens to the user the exact moment they are generated. This creates a severe user experience liability. If an AI streams its raw chain of thought reasoning and internal diagnostic text onto a shared screen during a client presentation, it destroys professional momentum. We face an inherent conflict. A presenter needs calm, definitive user interface components, while a power user debugging the system demands absolute transparency into the model's logic. To satisfy both requirements simultaneously, we implement dual-channel streaming using SignalR. SignalR is a software library that enables real-time, bidirectional communication between client and server. Through this, the language model emits two distinct parallel data streams. The first channel is the thinking stream, which handles the raw text tokens. This stream is routed to a discrete, collapsible side panel kept hidden by default. The language model uses this real-time thinking phase internally to evaluate context and decide which parallel backend tools to invoke. The second channel is the structured event stream, which handles the final outputs, sending discrete, structured packets instead of a continuous text thread. Once invoked, backend tools execute in parallel. Crucially, they emit typed metadata events back to the user interface, rather than returning raw text paragraphs. The front-end architecture listens specifically for these structured events. As they arrive, they instantly transform into cleanly formatted, stable candidate cards. Executing tools in parallel eliminates serial waiting, drastically lowering the time it takes to see the first useful card on screen. This creates an interruptible user experience. An operator can seamlessly toggle between the calm presentation mode and the deep diagnostic mode without changing the underlying pipeline. Progressive disclosure in enterprise AI is not achieved by generating long paragraphs. It is achieved by populating stable UI components asynchronously while isolating the reasoning. Stepping back, we can now see the entire decoupled pipeline, from the user query, through the search router, into the compute layer, and out through dual streams to the front end. Enterprise AI success does not depend on finding the perfect prompt or acquiring a larger context window. It relies entirely on systems architecture. The language model is a stateless compute layer requiring rigid infrastructure. On the back end, a deterministic search router exploits diverse databases without index duplication. On the front end, dual-channel streaming preserves diagnostic transparency without sacrificing interface stability. This resilient, production-grade state machine stands in direct opposition to the brittle, single-index wrapper demos that fail under pressure. While AI models raise the floor of what is technologically possible, classical architecture remains the ceiling of what is reliable. The most expensive failure modes are rarely hallucinations. They are a lack of continuity, catastrophic routing errors, and state management failures. Ultimately, the deterministic architectural guardrails engineers build around probabilistic models dictate whether a system survives contact with reality.